Well, welcome everyone. Today it's a pleasure to have Daniel Jafferis, who is a visiting professor here until the end of the year. And today he will tell us about the tensor model for 3D gravity.
Okay, well, thank you so much for the invitation to speak here today. It's wonderful being back here for a while. So today I'm going to tell you about some work that's partly based on this paper I wrote over the summer with Alex Bellin, Jan de Boer, Pranjal Naik, and Julian Sonner. And then we have some continuing work in progress with my student Lisa Rosenberg and with Gabriel Wong, who was a postdoc at the CMSA at Harvard and now is a. So I'll start with a little bit of introduction and kind of motivation, describe how I'll impose CFT consistency relations in a kind of integral over CFT data. So we'll do like an integral over CFT data of delta function of some constraints, but I'll impose it in some limiting sense. And then we'll see that expansion of this, what we can then think of as a random tensor model, looks like 3D gravity. So we kind of get the whole topological expansion out of 3D gravity from a starting point that looks like it's completely about CFT consistency. And there'll be some interesting role played by the sum over all topologies, and we'll see how it all fits together. So maybe one of the motivations of this question is to understand, what is the space of consistent CFTs? That's kind of the point of the Bootstrap program. And we might say, this is also dual by AdS CFT to the swampland question in AdS. So it's equivalent to the question of if I, have a CFT whose light operators have correlation functions that agree with a given effective field theory in AdS. And here I'm imagining a large C theory, but C doesn't have to be infinite, but some maybe large number. And then we might ask, is there an exact CFT which has those things as the light correlators? That's kind of the dual question to, is there a consistent UV completion of gravity, some gravitational effective theory in AdS? And around the AdS vacuum, we know the answer, or there's this equivalence between the two sides in the sense that perturbative solutions of the Bootstrap, perturbative in a 1 over C expansion, if C is large, exist for any effective theory of gravity in AdS. So there really isn't any constraint at the level of 1 over C perturbation theory around the vacuum. There's no swampland constraint. Everything works. There are some sharp naturalness-like bounds, like inequalities obeyed by the Wilson coefficients that were established using dispersion relations. So the kind of basic idea that that any perturbative solution to the Bootstrap, any EFT looks like a perturbative solution to the Bootstrap goes back to this paper of HPPS, but more recently in works such as this, there were some inequalities, but not, not ruling out order, anything that looked like some order 1 coefficient. So it sort of made naturalness sharp, but it didn't find, some big area of swampland in which there was a small landscape. And we don't really have a hint from these analysis of why, say that we think the set of CFTs is discrete, not having some enormous number of parameters. There's a huge amount of data to specify a CFT, all of the exact dimensions of every operator, including all of the operators dual to black hole microstates and all of the structure constants. We don't think that there are this huge number of moduli in any situation. Maybe there's some small dimension moduli spaces, perhaps some special CFTs, but so we don't really see from this where that comes from. But there's, of course, more to the theory in AdS than just the correlation functions around the vacuum. We could also study the thermal correlators of the CFT, which are related to the correlation functions of the effective gravity theory in a black hole background. But there again, well, it hasn't been studied as much, but in a sort of example of this, really in 1 dimension lower, some like in quantum mechanics, go to 2D gravity, we found that you get a consistent ensemble of CFT data. And now the reason why you get ensembles of CFT data is because if we discuss the correlation functions in a black hole background, the relevant microscopic information involves the 3-point function of 2 heavy operators and 1 light operator. So in other words, we look at the matrix elements of light operators between heavy states, and by stringing them together, we can compute correlators in the thermal state. And that's a huge amount of data. There's some entropy of the thermal ensemble, we might call it S, and so there's, e to the S high energy microstates, so we need e to the 2s matrix elements of the light operators, and we have a very small amount of data of the effective theory of gravity in the black hole background, so we're not going to nail them all down, but it looks like we get a consistent ensemble for any EFT. We don't really see sharp constraint. So somehow this picture suggests that the place where the sharpest constraints come from, the ones that we didn't impose yet, are from the crossing of the black hole microstates amongst themselves. That's something that's very hard to understand from the gravity effective theory point of view, right? It's like the statement that if we act with the black hole creation operator at two places at the AdS boundary, those operators should true. But it's not a very obvious, that looks hard to probe gravitation. But that must be where sort of these constraints come that tell you that you really have a discrete set of CFTs, and maybe lots of VFTs that rule the swamp line that must come from there. And it's that part of the constraints that what I'll talk about today might teach us something about. And maybe a simple example to keep in mind, especially relevant in what I'll tell you about this morning, is the question of, is pure 3D gravity in the swampland or in the landscape? So in other words, are there large C 2D CFTs with no operators below the black hole threshold other than the identity, Verma module? Or we could slightly relax this definition, and we could ask whether there could be large CFTs with only a small number of operators below the black hole threshold, and maybe not very far below the black hole threshold. So we could ask slightly different questions. And well, anyway, it would be interesting to know the answer to any of those kind of questions. And that's going to be related somehow. Now, another slightly different motivation, but you'll see how this connects to the first slide in a second, is when we have quantum chaotic theories, the features of the high energy microstates look pseudo-random. So, the earliest example is random matrix theory, right? Going back to Wigner in the 1930s, we have some complicated Hamiltonian describing nuclear physics, and it's very hard to solve it. But maybe it looks like you picked the Hamiltonian as a random matrix, and that already tells you something interesting. Level response certain coarse features are already reproduced just by the general idea of picking a random matrix. But we can ask a much more fine-grained question, much more precise question about this story of the pseudo-random aspect of high-energy microstates, which is in the following line. We imagine we have a specific theory. It has a specific spectrum. It's not random before. It's some very large number of infinite precision numbers is the spectrum. But we can randomize over the choice of microstates. So in other words, maybe we're interested in physics in a particular microcanonical band, but we don't know which microstate our friend is going to pick out of this band. And so that produces an ensemble of not knowing which microstate in the band we pick. And we can ask, if we make that kind of ensemble, what ensemble over theories is that equivalent to? Okay, so we were going to trade somehow an ensemble over the choice of which microstate in a band for an ensemble over the parameters. And strictly speaking, they can never be exactly the same, right? Because a single theory has some specific, infinite precision numbers, which are the microstate energies. But if we don't ask any questions that are, at say timescales associated, very, very long timescales associated to picking out individual fine-grained microstates, we will not be able to distinguish between some ensemble over theories and that pseudo-random. And we might say that the generalized random matrix theory hypothesis or eigenstate thermalization hypothesis, which has the the generalized, so that it has the largest chance of being correct, is that this ensemble over theories is like the maximum ignorance ensemble of the microdata, compatible with whatever EFT input we have, the long-range correlators that we wanted to match, and micro-consistency. Okay, and it's really this second part that I'm going to focus on for them. And this kind of generalized version of random matrix hypothesis applies to all time scales, including very long times up to the time scale where you see the individual Feynman layers. Then, of course, no random description could be valid. So this is a much broader range of potential applicability of that idea than the, saying that we have a Gaussian random matrix for the Hamiltonian or Gaussian ETH statistics. That will have a much narrower range of validity. So that's why I'm calling it generalized. We don't know that this is true, that all quantum chaotic systems obey this even generalized RMT ETH hypothesis, but I'd say that would be the thing that one would like to show. That could be true. And in our specific case today, we're going to discuss CFTs, and in the microdata of CFTs consists of the dilatation operator acting on the Hilbert space of primaries graded by spin, and the structure constants, the 3-point functions. And so these give rise to a matrix from the dilatation operator and a tensor from the structure constants, right, through a tensor. And so those are going to be the data of the game. Okay, so that's kind of the motivation. Now, and now we're going to see the connection of that ensemble question to the question of the space of CFTs, because we could imagine a very simple idea, almost a stupid idea, which is if we want to learn about all the CFTs, we can integrate over the CFT data and impose the bootstrap constraints with the delta function and any other input assumptions we have, if we're interested in some more specific question. And here, the only input I really take as a strict input is the existence of the identity operator. Okay. Now, we can, of course, impose this integral. So in principle, this thing localizes to the actual CFTs, because we think that, well, the actual CFTs are defined, in a sense, by things that obey the bootstrap constraint, or maybe we should say, Moore and Seiberg taught us that, 4-point crossing and modular invariance of torus 1-point functions is sufficient to imply all the consistency conditions for 2D CFTs. And so therefore, if we impose just those constraints, that's the full list, at least in 2D. In higher D, we're less sure. 4-point crossing is certainly a constraint on local operators, but maybe there's some other constraints on line operators, so we don't know what they all are precisely. So we're going to stick to 2D CFT. So if we impose all the constraints, we have an actual CFT. So in principle, this is some kind of sum and integral, localizes to sum and integral over the actual CFT. Yeah.
Does this nail down the measure, or
no?
It's localized on the space.
Right. So that's a very good question. I won't have much to say about that, but I think it's a very interesting. We could talk more about it later, but we might imagine in a favorable situation, in principle, for some specific exact value of the central charge C, which enters the constraints because we're 2D, this is Virasoro representations, there might exist either 0 or 1 CFT with that exact infinite precision number, and then the measure won't matter. You either hit it or you don't. So that's a little bit of an evasive answer. In a case where somehow there will be multiple contributions, this will weight them by some complicated factor, different relative factor, and I don't know what that factor is. But I would like to.
But you have to put some input, don't you? Is this the integral of the scaling dimensions? Is that the scaling dimensions of all pseudo-primary operators, primary operators? Don't you have to assume that there's a finite or an infinite number of primaries?
So here I have really in mind irrational CFTs with infinite number of primaries. What we could discuss playing this game for integrable theories, and I'll mention a little bit at the end, but that's not the main.
Okay, but the deltas and the the conformal dimensions of the primary operator.
Right, right. Delta is the dimensions,
Assume they're infinitely many.
and I will assume that, yeah, for now, yeah. I think the case with finitely many is easier in a sense, but less related to, less obviously related to 3D gravity, but easier because then it would be finite dimensional integral. Of course, in that case, we might not need to do it this way. We would just solve, we know the WZW model already, right? But I'll say something at the end where that might be interesting to study it. To learn something about the irrational case. I don't think we're going to learn any, well, let me not give it out. Okay, so now we could try to impose delta function of the constraints as a limit of e to the minus 1 over h bar square of constraints, where h bar is a new parameter. It doesn't map to anything on the CFT side. CFTs are when h bar is 0. If h bar is non-zero, we have some kind of approximate CFT, but that won't be really the thing of interest. Here, the interest is what you get by taking the limit, but we will approach the limit in some way and somehow reorganize the expansion in something magical. The end model. And so in this story, the thing you want to compute is not this integral. That's computing a measure factor that you didn't know about, but rather an expectation value of an observable. So suppose you wanted to compute some CFT quantity, like the CFT partition function on a hydrogenous curve. Then you write that as an expression in a particular channel decomposition, expression in terms of delta and C, and then you can evaluate that expression in this integral. So that will be like the ensemble average of the CFT partition function if there was the ensemble. So that's the kind of thing one wants to compute. The overall normalization cancels out, but of course it could be, again, relative normalizations, I won't say anything. So that's what you would like to compute. And well, another piece of kind of input, and again, most of the talk is going to be to explain this in detail. But another piece of input is, if we think about treating this integral as, at least the integral over delta, as like a matrix model, right? If we think about a matrix model, we usually organize it in something like a Toft expansion, and we have a notion of the leading spectral density. So the leading spectral density isn't in position that this density is given by that continuous density. That's not the right understanding, but that's kind of the first term in a series of terms. And here we'll take this leading spectral density to be the Carty density. The Carty density has a factorized form. It looks like a function of the left moving weight times a function of the right moving weight. And it starts at the black hole threshold of C minus 1 over 24. Okay, but that's just a pure CFT statement. And by the Carty spectrum, I mean the S transform of the Virasoro identity. So it's defined at finite C. Well, for C greater than 1 or equal to 1. Okay, so that will also be kind of an input, but we're in principle, we're not rigidly imposing that all of the eigenvalues are above the C minus 1 over 24 threshold, but if they are not, we'll think of that as the instanton correction in the matrix model where some eigenvalue tunnels out of the leading cut. So it's allowed, but that will be something subtle from this expansion.
Sorry, you said this in approximate CFT. Can it capture, for example, the conformal perturbation theory? Very close to CFT, but it's not a CFT.
Well, so this notion of approximate CFT is something rather strange that we don't usually consider, because the thing that's approximately obeyed here is the crossing equation, and the conformal symmetry is imposed exactly because we're just discussing the CFT data. The thing that's approximate is a crossing equation. The crossing equation is a consequence of locality. So it's so if we take this H bar to be finite, we'll be studying an ensemble of things that have exact conformal symmetry, but they're not exactly local. So it could mean like that the commutator of two things that look like they should have been local operators at space-like separation will be e to the minus c rather than zeros. That would be the object. I don't know if it's interesting, but that's what it would be.
We're discussing it as if you could define definite 4-point functions that don't have all the definite properties. But not having crossing, it seems to me that you don't know how to define a 4-point function.
Well, the way I would think of the structure, the way I would define the approximate CFT is I would say I take by assumption that the Hilbert space on the sphere, well, here on the circle, is, given by generated by the primaries plus descendants with whatever weights I said they had. And then I will say that I have some operators which act on that Hilbert space, labeled by the same set of data, where the matrix elements are given by Ci and Jk. But then they won't obey locality.
So then you do.
So then I do have a well-defined endpoint functions for any n, but it won't obey locality.
You've
Both
roughly-
five in a specific channel, they'll be different for different channels, so you just take them in.
Yes. But
So
so in other words, if we think about the CFT and Lorentz signature, we have the full set of data, but it's just not local, and the Euclidean continuation doesn't make sense. That would be one way to understand it.
I wonder if you can imitate that by considering the smearing of the operators regions as you do in, say, algebraic QFT. Does it fit into your framework, or is you have in mind something very different from that?
That's possible. Well, I don't have, I wasn't especially interested in the approximate CFTs. It's just an intermediate step in this discussion. We don't know. I'm not sure if they have their own life or something interesting, but indeed that could be a way to, maybe that's a natural way. I think it's something that we should kind of consider, especially in the context of CFT duals to effective theories of gravity in AdS, because it's not at all obvious from the point of view of semi-classical gravity why the black hole microstate operators should commute at space-like separation, right? That's not really a computation you can set up in semi-classical gravity. Only some smeared version, like, so if someone said there's e to the minus, 1 over g, 1 over Planck corrections, it would be hard to check that, right? So it's kind of relevant maybe in that context, but I don't know really what it would. Maybe it's not the name. Fine. So again, just to specify how we should think about this integral, it's like a triple scaled model. It's certainly double scaled because, the rank in the sense of the number of eigenvalues is being taken to infinity because I'm discussing irrational CFTs, and this h bar parameter is taken to 0. But there's also another scaling, which we'll see in a moment, related to the structure of the potential itself. It has some functions in it that become singular in this limit. So we take this whole thing as a combined limit. And as I said, in principle, in the strict limit, h bar goes to 0, crossing is opposed exactly, and either you find some exact CFT or collection of them or no solutions. If there were no solutions, then the total partition sum would be, exponentially going to 0, and something bad would probably happen to the observables, which are like the putative CFT partition functions. Or if you found the CFT, that will be the doubly non-perturbative completion of the model. But so far, this might sound like it's a very dumb idea, because this, first of all, C equals 0 is not a minimum of the potential, right? The potential here is crossing squared, but all structure constants 0 except the identity doesn't solve crossing. So C equals 0 isn't a solution. That's an expansion from the top of the potential, and the model is quartic in C's because crossing is quadratic in C's. So it looks like a strongly coupled tensor integral with very complicated functions of the weight. So that sounds terrible. And normally, if we have an expansion where e to the minus some potential and C equals 0 is at the top of the potential, we would try to find the minimum and expand around it. But that would mean I solved the crossing equations, and then I wouldn't have written the integral to begin with. Then it would just be completely stupid. So you might wonder why am I bothering this? Very dumb, right? And what happens is that, first of all, this isn't a completely specific expression. We can write the constraints in any basis. Take the square. We can take any positive quadratic form on the space of constraints and use that to make a function which is always positive and vanishes only if crossing is obeyed. And so there's an infinite number of choices because there's an infinite number of crossing equations, functions of parameters. But there's a very special choice where that constraint squared potential has some amazing integrability properties. It obeys some orthogonality relations, hexagon and pentagon identities, which are kind of descend to Yang-Baxter equation if you specialize some indices. So they're really like the usual integrability. And one can reorganize the expansion in a way that would seem very surprising from the point of view of just writing the stupid integral. And in the reorganized expansion, you put every diagram falls into some, so they're triple line diagrams because they have tensors, and they can be put into some topological classes, a little bit analogous to the Tufte classification of matrix diagrams, which are labeled by three manifolds. And not only that, with this special choice of the potential, every diagram assigned to the same topological class actually evaluates to the same function of parameters like C. But in general, a non-trivial function and each diagram will come with different powers of H bar and maybe numerical factors. That doesn't happen for matrix models. That's even more special. That's because of this integrability. So it's not only like it has a Tufte expansion, it has some kind of integrable expansion. So you can, every diagram evaluates to pretty much the same thing. And so then you can try to study the theory in the sort of Tufte expansion of the matrix model and this Feynman triple line expansion of the tensors and reorganize the expansion as an e to the minus c expansion instead of an h bar expansion. So if you pick a given term in the e to the minus, so why is it e to the minus c? Well, it's going to turn out that the terms in the potential involve e to the minus c, and the spectral density involves an e to the c. So like the genus counting parameter of the matrix expansion is e to the minus c. But the same thing will come from the tensor diagrams, but it won't be only integer powers of e to the minus c that appear. It's more complicated than that. But it's some kind of power expansion. And if you look at the coefficient of a specific term, it's finite as h bar goes to 0. And maybe a natural conjecture is that they're all 1, although I don't know how to prove this conjecture, but that would be the conjecture. But something illegal happened here from the point of view of the original integral, because what you really wanted to do was study the theory at fixed c, specific crossing equation, and then take h bar to 0, because that was just some fudge factor to impose a delta function. But here we reorganize, so that in other words, you should have taken this limit first at finite c, but here we reorganized it in the other way. We picked all the terms with a given order here, and then took h bar to 0 term by term. And the result of that is an asymptotic series. So we will find that the expansion, the power expansion e to minus c is 0 radius of convergence. It's an asymptotic series. And the ultimate fate of the limit is somehow a doubly non-perturbative question, since it's an e to the minus e to the c question, related to the sum over this topological expansion. So I think that's one of the interesting elements. So the rest of the talk is going to be me explaining this story. And then at the end, I might tell you a few generalizations of that. So that's where we're going to go.
Can you remind me again why the topological expansion parameter is e to minus c in the matrix model?
Right. Well, that's just because the spectral density of the Carty density goes like e to the c. Right. So in other words, it looks like so the Carty formula has e to the square root c times square root of the weight, but the weights start at c. And so therefore the least dense part of the spectrum has density e to the c. A very large weight is even more dense. But that means that, so that's like in a double scale matrix. So that means that the genus expansion is controlled by the least dense part, because that gives the biggest contribution, right? So that's e to the minus c. And so not only do you get some integrable numbers, but those numbers are actually exactly the same as the pure 3D gravity partition function. So in this topological expansion of the triple line diagram, so the plane where every diagram gets mapped to some manifold, the answer for the diagram is the 3D gravity partition function on that manifold. And at least for the part of the story that involves just the tensors, we can, explain this to you by basically matching the basic building blocks, like the pieces that look like the vertex and the propagator and so on, to 3D gravity amplitudes and using the logic of Virasoro TQFT, which gives some, beautiful ways of computing 3D gravity amplitudes, and it makes it almost obvious that every diagram evaluates for the associated Virasoro TQFT amplitude, because it's like a TQFT, it obeys gluing rules, which are just turned into the gluing rules of Feynman diagrams. So there are a few pieces of the story, but I'll explain. So at the end of the day, you get quantities that look like sum over 3 manifolds of some 3D gravity partition functions, which depend on parameters like C, and then some other function of the manifold in H bar, which doesn't really have to do with 3D gravity. And if you want the H bar goes to 0 limit, the conjecture is that all these F's become 1. Okay, so that's sort of the general structure. Now, there is, as I said, of course, also the integral over the weights. That's like the matrix integral. There's still some details there that we have yet to iron out.
And so what is the Z of 3D gravity?
Well, we could say for most of the manifolds, this is a Virasoro TQFT partition function. Probably ever in general. That's what really comes out. But I think that's equal to the path integral over the.
And so this is the sum over compact oriented or not 3 manifolds.
Yes.
Don't worry about too much about the orientation, but this is the sum over diffeomorphism classes.
Not compact, that's
Three
right.
manifolds.
Right, so if I was just evaluating the partition function of the ensemble, then it would be compact 3 manifolds, but actually I'm not sure what that number is supposed to equal. In a sense, it's because I don't know what's the weight factor. Assigned to CFTs,
That was one question I had.
but
But this is the sum over diffeomorphism types of compact 3 manifolds.
if I was evaluating the partition function, they would be compact, but if I'm evaluating an observable, so I'm computing what would have looked like this genus 2 partition function of the CFT made out of 2 structure constants, then this will be a 3 manifold which has the genus 2 thing as a boundary. So in general, it's going to be a sum over 3 manifolds which have as a boundary the associated Riemann surface, the Riemann surface associated to the observable that you inserted, just like in a matrix model. So if we would just compute the partition functions, closed Riemann surfaces, but if we insert traces, then they have.
That's fine. What I'm trying to get is that you're summing over the diffeomorphism types.
Yes, yeah,
Are
exactly.
you weighting these 3 manifolds? The weight is just literally what you've written there.
Well, so as far as I know the weight, it's a function of the parameter H bar, so it could be anything at the level of this formula. I didn't say what the weight is, except that this function doesn't depend on C.
Supposing the 3 manifold that's a hyperbolic matrix.
Yeah.
Do you have any idea how these things grow with the volume?
Well, yeah, so
Normalize it to R equals -1.
right, so at large C, then the 3D gravity partition function goes like e to the minus C times the volume.
E to the minus C to the volume. And what about this F?
F doesn't depend on C.
How does it depend on the volume, the large volume?
Well, the conjecture is that as H bar goes to 0, F is simply 1. Or maybe a symmetry factor.
Okay, but
But it didn't prove this conjecture.
the number of 3 manifolds, number of hyperbolic 3 manifolds, number of diffeomorphism types of hyperbolic 3 manifolds of hyperbolic volume V is approximately like V to the V.
Yes, and that's exactly what's an asymptotic series. And so the question of what's in a way, one of the lessons here is that in the sum over Riemann surfaces, if we were doing 2D gravity, 2D string theory, it's also an asymptotic series, and the non-perturbative completion is the matrix integral of specific contour. Somehow here, the non-perturbative completion of the asymptotic series summed over the 3 topologies is like a specific CFT2. So it must rigidify the integral because at the end of the day, at least in the limit H bar goes to 0, Because in that limit, at the end of the day, you impose the strict constraints. So it has a very different kind of non-perturbative completion. If you would have studied the theory without taking h bar to 0, then it might be more like, then it would be a specific choice of contour for this matrix in tensor. Okay. The reason why you got an asymptotic series is exactly because you reverse the order of the h bar and c expansion, right?
No, I think you said this, it's an asymptotic series in e to the minus c.
Right, so it's possible that if you didn't take h bar to 0 first, that it would be a convergent series.
What about what I just said about e to the?
Well, it depends on the behavior of the f, right? I don't
That's
know.
why I asked what f is doing that.
Right. So, these questions I don't know the answer to. I would love to know. I think if we knew the answer to those questions, it will really tell us, the answer to knowing the answer to that will tell you whether there exists a certain specific CFTs or not. That's about kind of the e to the minus e to the c completion. So those are the most interesting questions, but I don't know. I only have the questions, not the answers. But I can tell you a lot about the e to the minus c expansion. But even in that story, there's some piece that we're still ironing out related to the matrix integral. And let me just say a little bit of why there is something subtle there. Just as an example, the most basic thing that comes from the matrix integral, aside from the leading density, the disk, is the annulus. The matrix annulus diagram, that's, like the double trumpet of Sad-Shanker-Stanford, if we were thinking about the JT gravity story. In the 3D case, that's like a manifold T2 times an interval, right? If we just compute the trace e to the minus beta h, where h is delta, right? Then that's the manifold that's like two copies of trace e to the minus beta h, like 2-point function of spectral density, that's T2 times interval. And that kind of manifold, which is not hyperbolic, the 3D gravity answer, in this case computed by Collar and Jensen, disagrees. It's not equal to the versorial TQFT computation. And this is really due to the mapping class group of 3D gravity. It's completely analogous to something that happens in 2D JT gravity. If you would compare the JT gravity partition function on the double trumpet with the 2D BF theory partition function on the cylinder, they don't agree for essentially the same reason. It's like the fact that if you're familiar with it, in the SSS story, Sad-Shanker-Stanford, there's a BDB measure in the gluing of geodesic cuts with length B, and the B in the DB comes because there's a finite range of a kind of angular gluing. But if we would study the TQFT, it would say that the range is from minus infinity to infinity. So we would get and measure infinity dB, not B. That's what the versorial TQFT produces. And just to point out, so that doesn't say what the tensor model will give, but it maybe suggests there's something a little more subtle there. And we mostly understand it, but I don't want to present it because it's not completely understood. But I'll just point out that the versorial TQFT result, like the 2D BF theory result, is just like a delta function in energies. That's kind of natural because anything times an interval is just the inner product of the Hilbert space from the point of view TQFT, kind of has to give you delta function. And that would correspond to Poisson statistics of the eigenvalues, right? It would say that there's no finite range eigenvalue interaction at all because the correlation function is delta functional. So that sounds very unphysical from the point of view of random matrix theory. It's a bad answer from the random matrix theory point of view. So something is a little more complicated here, and I ultimately think the matrix integral will give really the 3D gravity answer for these kind of manifolds. When a 3D gravity answer disagrees with versorial TQFT, it seems like an integral over matrices will give the gravity answer. And there's still some details for them. The only part of the integral over delta that I'll actually use today is the leading result, which would be the SL2Z sum over solid tori. In other words, the sum over BTZ and all of its SL2Z images. Okay, so that's the only part I'm gonna use, and actually, I'm only gonna really analyze things manifold by manifold. So even this SL2Z sum has a divergence, which is usually regulated by zeta functions. I think the matrix model has something to say about that, but I won't discuss that today, also because of lack of time. But I'll just discuss things manifold by manifold, and everything is okay. Well, maybe I alluded to this already. I think I'll just sort of skip this slide, but it's just drawing the analogy of this to the Sad-Shanker-Stanford story, which is sort of an analogous thing where we have an ensemble over quantum mechanical Hamiltonians, which is related to JT gravity. And there is a close connection because, after all, some limit of 3D gravity looks like JT gravity. 3D gravity on a circle and some sort of scaling limit looks like JT gravity. So there's some connections there. I hope this is the correct version of this talk because I thought I deleted this slide. But I transferred something from the computer because mine didn't connect with so. Let's hope there's not a blank slide. Somebody, that would be unfortunate. And I should also mention that, there's been a lot of interesting work, especially by these authors, but also others, on connecting tensor models, integrals over CIJKs to 3D gravity. I think their perspective was slightly different in that they started by saying, the Cardi formula gives the asymptotics of the spectral density at large weight in any CFT. And if by sort of a similar logic, if we looked at the 4-point function IIJJ, operators IIJJ, and that has the identity operator contributing in one channel, and in some extreme kinematics, the identity dominates there, the OPU limit in that channel, that has to be matched by something in the T channel, and that gives you some asymptotics for what CIJK is, because now I have IJ fusing to K, which they showed looks like this, where C0 is basically the Liouville 3-point function given by the DOZZ1. So there's no Liouville theory here. It's just a statement about what you need to satisfy cross-sign. Okay, but it just comes out that the answer is the Liouville 3-point function. We're not saying the CFT is Liouville. It's definitely not, because our CFT has the identity operator, and the spectrum is like Cardi, whereas at leading approximation, whereas Liouville doesn't have the identity operator, and the spectral density is more like the Tench function, not the Cinch function. And then these authors constructed an associated Gaussian ensemble for the CIJKs with this variance. And they noted that the answers from that reproduce certain answers that agree with 3D gravity computations for various kinds of handle body and sort of Euclidean wormhole topologies. But they didn't produce all 3 manifolds. It was a very simple or very special class of 3 manifolds. I kind of made this point already, so I won't belabor this, but in quantum mechanics, any Hamiltonian is allowed, right? There aren't any constraints. So it's very natural to end up with integrals over the microdata, and the non-perturbative completion is the integral because there isn't anything special from the point of view of self-consistency by any specific Hamiltonian. But in higher data, it's very different because of locality. So, 4-point crossing and torus 1-point modular invariance pulls some strict constraints, and we don't expect there's ensembles with these e to the s parameters. So this is definitely the previous version. So there's probably going to be a blank slide. That's really too bad. Okay. Let me see if that. Oh, I'm just missing some slides. Okay, I see. Okay, well, maybe that's okay. I might not have gotten to them anyway, but that's fine. Or we could waste, I don't know how much, probably it won't bother to waste the time to get the other one. This is not a blank slide, that would be nice. Anyway. Right, so in this Gaussian ensemble, there, the expectation value of crossing vanishes. But individual instantiations violate crossing law. So they don't look like even approximate CFTs in that sense. So you can look at the variance of crossing. Like I could write the genus 2 partition function in this channel decomposition, or in this one, take the difference, take the square, and then integrate over the ensemble. And if one did this in the Gaussian ensemble, this side squared has a contribution from this genus 2 wormhole, so does this side squared, but there's no cross term because the index structures don't contract in the Gaussian model between something contracted this way and something contracted that way. So you find some big answer for the variance of crossing. And in order to cancel it, you could think you might add a chordic moment, which would be the thing which, when you contracted it with an S-channel block, equals a 3T channel block. And then you'll be able to cancel it. And the thing that contracts with an S-channel block to give a T-channel block is the crossing kernel, but there's some factors of these DOZZ formulas, so you end up with this thing, the Wigner 6J symbol. This thing has a tetrahedral symmetry of exchange of the arguments. This doesn't, you have to multiply by those. Yeah. Now, we wanted to do something a little different. We wanted to just impose crossing sort of through some limit that looked like a delta function. What basis should we use? Well, we can, if you took the crossing equations, you usually think it was a function of cross ratios. We can expand it in terms of the S-channel principal series. So if we take S-channel blocks and expand them in terms of S-channel blocks, we get a delta function. And if we take T-channel blocks and expand them in terms of S-channel blocks, we get this crossing curve. Now, there's first a piece of notation. It's kind of natural to write things in terms of this variable P and P bar, which are like the Liouville momentum associated to a given weight, but you can just think of P as defined as the square root of the weight above the universal threshold. That's a very natural variable. But then more importantly, in this way of thinking about it, there's something a little funny sometimes about this delta function, especially because we have here the sum over the physical spectrum, not the principal series. Now in 2D CFTs, if we talk about Virasoro representations, there's an overlap between the physical allowed spectrum and the principal series, which consists of real weights above the black hole threshold. In higher D, they have no overlap. Well, the point, delta equals D minus 2, but otherwise, no overlap. But we certainly have at least the identity operator below the threshold. So in that case, this delta function is an off-contour delta function. What it really means is something that we have to understand as a distribution that makes sense when integrated against functions of P that have the analyticity properties of the blocks as functions of P, which are much more constraining than smooth functions of P. So it's a little bit like an analytic function, and then of course the delta function off the real line makes sense. That's actually not going to matter. But to write this equation, this means the crossing kernel is defined by Posnat and Teschner, analytically continued sometimes to below threshold weights. That's just a continuation of the function. This is sort of a more subtle analytic continuation. But also, we should understand this equation as some limiting procedure where this delta function is smeared, and then we can take a limit at the end where we would get an exact delta function, because this thing is going to be squared and put into our potential. So the potential for this, so the tensor model has this form. Here I wrote things in terms of L0 and L0 bar, rather than delta graded by spin, which is maybe more natural if we think of terms of plugging in the leading density, since the leading density is factorized as a function of weight H and weight H bar.
So what is L0? Is L0 a vector or matrix?
It's a matrix. Yeah, L0 and L0 bar are matrices. And the eigenvalues are the weights.
Yes, that there are permission matrices and there are eigenvalues of the weights.
Right, and I mean L0 and L0 bar as matrices acting only on the primaries. So they're just representing the weights of the primaries. So they're eigenvalues of the weights of the primaries. And then we take the square of the previous expression, integrate over the principal series value here, which I call PS, and end up with this expression. And so there's a kind of trivial contraction structure, this one, which is like the S channel times the S channel, or equivalently T channel times T channel. And it has a delta function that sets this weight equal to that weight, and then some copies of these DOZZ expressions. And then we have the more interesting one, which is T channel times S channel, which gives the tetrahedral contraction of the indices. And that's multiplied by the 6J symbol and also some C zeros. And this combination has full tetrahedral symmetry of exchange of the weights. Now, the fact that that appears is very natural somehow, because if we, this combination of tensors has tetrahedral symmetry, so it should be multiplied by the group theoretic object associated to the tetrahedral contraction of Wilson lines, and that is the 6J sum.
So, sorry, what is this V for that we're looking at? This is the
Well, this is just the
result of
this is the result of the square of this
square of that.
integrated over PS. And then there's one special case, so the identity operator we include explicitly. We're not integrating over the weight of the identity operator, include it explicitly. So that gives a term here from this piece, which turns out then this thing simplifies and it gives this expression. So we have a propagator, which with this kind of contraction structure. It's a propagator because it's quadratic in C. It has the wrong sign, but that's our propagator. It has the wrong sign because C equals 0 isn't the solution of crossing. And then there's also modular invariance of torus 1-point functions. And that can be similarly written in terms of a modular inversion kernel. And one takes the square of that as also part of the potential. And modular invariance is 1-point functions is linear in the structure constant, involves C, I, J. So when I square it, I get something quadratic with this contraction structure. And I don't treat this as part of the propagator. I treat it as a quadratic interaction vertex. Turns out that's the right thing to do. And then there are some pure matrix pieces. If I just looked at the, S invariance of the torus partition function, and those will give me an expression like this, and I won't have much to say about that today. So I really wanted to focus on the tensor part in the remaining few minutes. Now, again, the kind of conjecture of which I will partially explain why it's true is that term by term in the topological expansion, in this limit when we send h bar to 0 and so on, and the spectral density, becomes an infinite cut and so on, we get exactly pure 3D gravity, including the sum over all of the three-manifolds, all the hyperbolic ones, especially. The ones that aren't handle bodies, we don't usually know even how to include, but these beautiful papers on Verlinde QFT kind of taught us how to compute those partition functions on complicated hyperbolic manifolds. And the basic building block, one of the basic building blocks, the most versatile one, is this 4-boundary wormhole that's associated to the 6J vertex. So we have this chunk. It's simple as a 3-manifold, just looks like a 3-sphere delete 4 balls, but then it has this interesting arrangement of Wilson lines. You could think about it a little differently. You could say I just take S3 and draw a tetrahedron in it, and then I X-size the 4 vertices. And so because those are the 4 walls that I X-size. And the Verlinde QFT or 3D gravity partition function on that manifold is the 6J sum.
There's a manifold with conical singularities.
Well, here it's a Verlinde QFT amplitude. I'm going to tell you in a moment what I do with the Wilson lines. Yeah. This is still sort of an intermediate.
Okay, so
this is an intermediate step.
Weights.
This is a manifold dressed with lines, and it can be assigned a Virasoro TQFT amplitude. But in a moment, it will turn into a smooth manifold with no lines. I hope I didn't lose some. Well, so one of the slides I lost here was that another way you could think about this is just to use the Verlinde inner product on the space of conformal blocks. So if we take the overlap of the S channel and T channel blocks in the natural measure defined by their Verlinde inner product, it gives precisely the 6J symbol. And that's very natural from the point of view of this Virasoro TQFT. It's like a splitting of the manifold given by the S channel insertion of Wilson lines into a thing with the boundary given by a sphere, and the T channel insertion of Wilson lines and a ball whose boundary is a sphere. You glue the two spheres along those. You glue the two balls, that makes an S3 with the tetrahedron in it. And the only difference is that here, I never have triple junctions of the Wilson line. Right? That's not really an object in the tensor model. I'm supposed to, that's where the structure constant is supposed to go. Excise those, and then I glue the pieces together with the propagator, which looks like an S2 times interval with 3 Wilson. So that's kind of the structure. Now, one very important point is that, it seems like something came out weird here because the propagator has a factor of h bar and also the wrong sign. It doesn't sound very nice, but it's very similar to what happens in the following ordinary integral. So just to demystify that, if we did this quartic integral, in the limit that h bar goes to 0, of course, it simply imposes that x squared equals v. So expectation value of x squared will be v, assuming that v is a positive number, okay? But if we think about it, if we expand this potential out, it has a quadratic term with this factor. And so it looks like if I did, Feynman diagrams, it's integral, that the propagator will have a minus sign and a factor of h. But if I resum the diagrams, I will get the right answer because it's the ordinary integral, or, the correct answer is a solution to the Schwinger-Dyson equation, right? Which look extremely simple for this integral. That's really the same logic that happens here. And normally this kind of thing is not something you do practically, but here, because every diagram assigned to the same topological class evaluates to the same answer up to the factors of h bar, it's really the same as the summation that appears in this integral.
When you do Feynman diagrams, you're supposed to expand around a saddle point. Why would you want to expand around 0? It's not a saddle point.
Well, it is a saddle, but it's an unstable saddle, but it's a local maximum of the potential, not a minimum. And since it's an ordinary integral, it works because we don't have spontaneous symmetry breaking, right? It's just an integral. Now, normally that would be a stupid thing to do, but the reason why we want to do it is because here, the minimum of the potential is the solution to the crossing equation. So that's the thing that we don't know. So the whole point is to reorganize the expansion in a way that might sound crazy, but the result of that reorganization is something beautiful. Okay, well, I'll say this and then I'll go
ignoring other saddle points right there.
So
In your toy model, you're ignoring other saddle points.
Well, so in the toy model, of course, you could
So
solve.
the quartic, so if we take a derivative, we get a cubic, which has more than one root.
Yes, it is. Of course, it has, there are 3 saddles, the one at 0, which is local maximum, and then the 2 minimum, right? But in the limit that h bar goes to 0, the answer localizes to the actual minimum, and there's no contribution from the local maximum. But you can reproduce that answer by the summation of the diagrams based on the local maximum, even though normally we think it's a stupid idea, but it does give the correct answer. Or, the Schwinger-Dyson equations based on the local maximum are still obeyed by the non-perturbative answer. You have to be, right?
Yeah, I'm not sure if this remark is helpful, but there would be an integration counter that would be dominated by the expansion.
Oh, that's true. Yeah, along the imaginary axis.
And it is also true that the Schwinger-Dyson equations are valid for each contour.
Right.
They're related comment, if you change the potential such that this is a local minimum.
Yeah.
And then the expansion around that is the same expansion.
Yeah.
So if it's convergent, it gives you the answer.
Right. Well, the Schwinger-Dyson equation, if you truncate to bubble diagrams, the Schwinger-Dyson equation is quadratic and it has two solutions. And which of the solutions you get depends on the contour or on whether V is positive or negative, however you want to think. Okay,
That would be like a large n approximation to that equation.
that would be exactly, yeah, like an enlarged vector model, sum over bubbles. Okay, anyway, I didn't really want to think about that integral, but okay, I hope the integral would demystify it, but it worse. So again, to reiterate, the basic building blocks here produce kind of simple manifolds. They only have these two-sphere handles, and then they're addressed by some, they're threaded by various Wilson. But all the Wilson lines are ultimately closed. So I had in mind that we were computing something with an external observable. So some of them are closed to the external observable, but the external observable should be something like the genus 3 partition function of the CFT written in terms of CFT data. So it doesn't have any dangling indices. Just like in a matrix model, you compute expectation over products of traces, not like some specific matrix element. So all of the index lines, the Wilson lines are just like index lines from some point of view, and they're ultimately all closed, although some close through the external observer. Now, the leading thing to do is to put in the Cardi density, and then there's also a whole series that sums over SL2Z images of the Cardi density. And that's simply, if we have a completely closed line, an internally closed line, that doesn't go through the external observable, that just putting in the Cardi density geometrically corresponds to doing toroidal surgery, where we cut out the loop and glue it back with an SL2Z transform, the S transform, if we just put in Cardi. The ones that end on an external insertion, you don't do that kind of surgery. You just cut out the Wilson line and you don't glue anything back. You just leave it as a whole. Then it has a component of boundary which looks like an annulus. Originally, the external operators are allCijks. So because they're external, they're boundaries that look like two-sphere with 3 punctures, but then you glue the punctures along annuli and that produces the boundary to look like the Riemann surface it's supposed to. But now the annuli that glue together those spheres can be going through the rest of the 3-manifold in very general ways. It can be knotted and linked. So in that way, you get very complicated 3-manifolds. And in fact, it's really easy to see that, let's say, at least in the case with no boundaries, you generate all the compact 3-manifolds. I couldn't really draw it very well on the slide, but the basic idea is, that if we draw the vertex like this, we can think of this as an outer 2 lines and these as inner 2 lines. And now, when you glue 2 of them together, you can do it with any S3 permutation. But a very simple way of doing them is to just draw them as glued as they are as rotations in the plane. That's one choice. I only need to show you that I can make all the manifolds one way. And so if I glue them like that, then the next one will be glued here, etc. And so in the end, I'll have closed loops like this. So the kind of exterior lines will all form simple closed loops. But remember that in the 3-manifold, this thing was inside of a tube in the 3-manifold. So there's a kind of handle in the 3-manifold in the middle of each of these loops. But if I do the Cardi surgery on this thing, it simply deletes the handle, right? The meaning of the handle in the middle, right? So I'm supposed to draw this around it, where the red line here, although it looks like a circle, is supposed to be, the cross section here is a 2-sphere, right? So this thing makes a kind of 3 handle. It's a terrible picture, but hopefully it's clear. And the meaning of this handle is that the white circle here is not contractible, but if I do the S surgery on it, it makes it contractible, and the effect is to simply delete both of them. So if I do that on all of these, everything is deleted except the middle lines. But the arrangement of the middle lines that each vertex could go over or under, it's my choice. It depends on how I oriented the vertex, and therefore I can get an arbitrary link because I can do any configuration I want. And then Licorice's theorem tells you that the surgery on that gives all the manifolds. It's a little more complicated if we have boundaries, but I don't have time to describe.
Are you saying that you get all the non-compact three manifolds?
No, so this is a story for compact manifolds. And then if I have external observables, I get manifolds with boundaries. And that's slightly more subtle, but I get almost all of the manifold boundaries, I get all the hyperbolic ones, and exactly which others is a little more complicated. Okay, but anyway, I generate a great many three manifolds, and in some cases, it's literally all.
The procedure of surgery, does it have a counterpart in the approximate? That's extra operation. So is there a counterpart on the approximate CFT side? Or?
Well, I mean, let me, I'm not exactly sure how to answer that question, but maybe this will answer it. So if I'm in this ensemble, this tensor matrix ensemble, I compute expectation value of some CFT partition function. And you can think about a finite H bar, it will be an approximate CFT partition function. And it's also labeled by some moduli. Then the answer looks like a sum over three manifolds whose boundary is this Riemann surface of the 3D gravity partition function, which depends on C and the moduli, times some function of the manifold in H bar. So the approximate CFT story is just to take this function to be the one for H bar quinine. But it's exactly the same sum over three manifolds. So that it's completely decoupled, these two pieces. I mean, they're coupled by the sum over three manifolds, but term by term, they're decoupled, right?
Right. So you're going to change the kind of weight separately.
Right. So the approximate CFT story will change the relative weight of the three manifolds. Let me try to just finish up. So if we took this conjecture that limit as h goes to 0 of f is 1, that will be the same thing. We really just get 3D gravity, sum them all coefficient 1. Or maybe 1 over the symmetry factor, like that will have some discrete symmetries. We should be well, that seems like a very, very hard thing to check because there's an infinite number of diagrams that contribute to each three manifold. Let's sort of clear here because since the operation of the surgeries can delete the holes, I can put chunks together and then simplify them down. So many diagrams get mapped to the same manifold, infinite number of diagrams for each manifold. That's why this is a complicated function. And it has to do with the combinatorics of these chordate triple line diagrams. So that sounds terrible. But we can test the conjecture, right, by checking whether it would obey the Schwinger-Dyson equations. So now, of course, there are infinitely many Schwinger-Dyson equations. Maybe the simplest is for the 2-point amplitude. So we might say the exact 2-point amplitude, we conjecture is the sum over all three manifolds with the two externals with equal weight, should be equal to what we get by gluing some diagrams. So there's the 2-point vertex, which I pulled onto this side just to make it simpler, of which has these pieces, which look like some manifolds. And then we get the 4-point vertex glued into the full 4-point amplitude, whatever it is. And this thing will include also, I should have drawn the red out to here because it could include this pieces where these endpoints aren't all connected, right? So we can check whether the sum over all of these with equal weight when glued into this chunk equals this. So this is like a purely topological combinatorial state. You don't have to check an integral. It doesn't matter whether we studied what the value of C is. It doesn't matter whether we have Virasoro or super Virasoro or Chern-Simons. You know, it's just a purely topological or combinatorial statement if true. And even this equation is really an infinite number of things to check because we have a sum over all manifolds. But you can look at the term on the right-hand side that would come from the simplest thing, which is just the S2 times interval with 3 lines. And then there's a finite number of chunks that when glued into those give that specific manifold. And so there is some finite pieces that can be checked, and each piece you check gives you more confidence that the statement is true. So, we check the simplest thing. But even that's not completely trivial, because actually quite a few manifolds, which when glued into one or the other, says that basically there's one more manifold that when glued into this chunk gives this simple manifold than there is glued into that chunk. Because if the coefficients are all one, right? Okay, so that's actually turns out to be true, but it's very hard to prove this statement. And I don't know if there's an easy proof, but I don't know.
Are there minus signs in this formula?
There are minus signs because the vertices have a different sign. Right, the one that came from S channel squared has the opposite sign as the cross term. And there are no factors of h bar in this equation because I took the limit h bar goes to 0. So I would have had a bare propagator term, but that's proportional to h bar. These have propagators glued to vertices, and the h bar times the 1 over h bar cancels. So these equations actually cannot fix the overall normalization, only the relative coefficient between different manifolds. But I think we might be able to fix the overall normalization by noting that we are in h bar goes to 0 limit imposing crossing, and then we can use the logic of previous work on this subject to show that, in some kinematic regime, the answer has to match the Liouville C0 function, and so that says that the coefficient there has to be 1, and then if all the other relative coefficients work, then you're good. I'll skip that. I'll just say a brief word here. The e to the minus c expansion, as I said, it's an asymptotic series. The number of manifolds grows faster than exponential, v to the b, I guess, pointed out. And but the action is the square of a constraint. So somehow, at least in this h bar goes to 0 limit, it's like the non-perturbative completion would be a specific CFT 50, which probably requires some or maybe many operators pushed off the original contour. And that depends on whether or not you believe that there exists series that are pure 3D gravity according to Bootstrap definition. I don't know the answer, but the answer is contained in the doubly non-perturbative completion of this sum. And that seems like something we might be able to learn. I think I went a little bit too late, so I'll just stop there.
All right, do we have any questions, comments? There's questions there.
Yeah, so could you go back to 19, slide 19, the bottom? Yeah, so, okay, I think you might have said this, but the three manifolds are not necessarily connected, right?
Right.
So the limit as h bar goes to 0 should be like 1 over n factorial if you have n copies and you're disconnected, disjoint sum of, you have n copies of one kind of diffeomorphism type, presumably you should get a 1 over n factorial for each kind of diffeomorphism type.
Yes, but so that's a simple example of a symmetry factor.
Well, but there's some debate about what are the right symmetry factors.
But I think that particular one is harder to test because when I compute here this, so I really should have said, so if I'm computing the expectation value, it means that I divide it by 1 over z, where z is just the integral over the tensors. So therefore, only manifolds which are connected to the boundary observable contribute. The other things are like vacuum bubbles, and those cancel between integral over the tensors of the observable divided by integral over the tensors of the one, right? So those disconnected chunks would not appear in this sum if I'm talking about the.
But let's see, does F know about sigma? Does F of M3 H bar know about sigma?
Yes. I mean, sigma is part of it.
Because sigma need not be connected either. And again, you have the same.
Yes. So that's an example where that would arise. Yes, if sigma was disconnected, there will be contributions that are disconnected.
So then another question is, supposing I take M3, which is just the product of a circle and a remote surface.
Yeah,
Isn't the 3D gravity partition function infinite?
yeah, so that's related to the matrix part of the story. So when you, so in the, that's related to the part that I don't fully understand. When you compute the, right, so if we did the integrals over the tensors first, we would get those simple manifolds with lines, and then we should really fill in the lines. We should think of the lines as fundamental index things in the matrix model. Now, the leading thing is to fill them with a disk, and that's what I discussed. But in principle, you should also insert annulus and higher genus things, which have in general genus G with n boundaries, which can be connected or not connected, right? If I have n closed lines. And the associated three-manifold is basically sigma G times a circle, right? Although sometimes there is SL2Z along the annuli, you could do SL2Z transforms. So it's a little bit more general than just sigma G times circle with a cipher map. And so to really understand that part of the story, you have to get completely straight to the integral over delta or L0 and L0 bar, which I haven't 100% understood. But I think often the 3D gravity, so for an example would be T2 times the interval. But actually the 3D gravity partition function on that manifold seems to make sense.
No, but I want to do it a compact Riemann surface times a circle. Because then I know I'm taking the trace over the Hilbert space, and I know that.
Sure.
So then the 3D gravity partition function is infinite.
Sure. I agree, but that will anyway cancel in, you know, if I compute these expectation values, that's a closed manifold that won't.
Greg might be able to find something with boundary with the same street. So in other words, a circle times a Riemann surface with boundary might have the same issue.
Right, but they're actually sometimes, right, so that an example could be a circle times an annulus. Okay, but somehow circle times an annulus seems to give a well-defined answer, not the divergent answer. It's because of the mapping class rule. So the Virasoro TQFT partition function on circle times annulus is divergent. And you can think about it indeed as the trace over the annulus Hilbert space. But the 3D gravity partition function gives a different answer. I mean, it's related. Well, maybe we should talk about it afterward. But somehow the 3D gravity partition function is finite there, even though the TQFT partition function is infinite. It's because there's extra identifications that actually make the answer not the trace over the Hilbert space. So the Euclidean gravity path integral on T2 times the interval is not equal to the trace over the annulus Hilbert space, somewhat surprisingly.
So Greg's infinity would definitely be there in Chern-Simons gauge theory.
Yes, absolutely, absolutely, absolutely. This a very similar thing happens if we would discuss the interval times the circle in 2D gravity. So the interval times the circle, you might think is the trace over the Hilbert space on the interval. And if we were discussing 2D BF theory, we would get infinity as the answer. But actually the 2D JT partition function on the interval times the circle is the double trumpet, which is finite.
You can get the measure from the F theory, but the integration region you have to divide by that.
That's exactly the point. So the same story applies in 3D, and I think that will probably make many of those answers actually finite.
I'm not sure if this comment is relevant, but so you are trying to have a situation where you're trying to obey some constraints. And I think in your discussion, you basically assume that all the solutions of the constraint look basically the same. All the C's are kind of similar, or at least some configuration. But if there were many different solutions that look different, I mean, there are many situations where potentials that have minima that are all very different from each other. And, so in other words, you could have you could wonder whether there might be a spin glass phase of this integral, because it's somewhat similar type of problem, and people discuss constraint satisfaction problem. I wonder if there's a way to diagnose whether you have either that case or a case where they all basically the same.
That's a fascinating question. I don't know. Yeah, I'm not sure. Well, all I can say is that one could try to adjust this model by putting in some light op. So I think in a case where there aren't any light operators, they all sort of look the same. That would be my guess, in the sense that I would imagine that the partition function of a CFT dual in that sense to pure gravity would all be, if there were many such CFTs, I would imagine that their partition functions would be all pretty similar, almost by definition. But if we talk about solutions of the constraints which take many, or importantly, which take many operators outside of the leading cut, so in other words, take operators below the black hole threshold, they will be much more different as solutions to the constraints, right? And we could try to access such theories explicitly. One way to do it is to simply say that you have some specific below threshold operator, just like we did for the identity operator. But a little bit more natural is to insert a determinant operator into the partition function, which gives a potential that pulls one of the eigenvalues out of the cut. Because from the point of view, if you want the diagrammatics to still match 3D gravity, it's not very natural to exactly fix an eigenvalue, because it says there's no e to the minus c corrections to the eigenvalue, if you like. This is not. And then the diagrammatics won't directly relate to 3D gravity, but if you would insert a determinant operator, it probably does. So that's familiar from matrix models. Right? Inserting a determinant operator leads to a nicer Tuft expansion than simply fixing an eigenvalue of the delta function. And similarly, if we have, like, say, a light 3-point function, instead of fixing it rigidly, it's more natural to put a source term in the potential, like a e to the minus fc light times the number, and that will generate diagrams with a bulk triple join. And then, but you'll sum everything, and so that won't be the exact 3-point function, but it will give you a kind of leading order contribution. And I think, I haven't worked that out yet, but I think it would probably lead to something that looks again exactly like 3D gravity expansion with whatever those light states are. So the fine-grained question of what exists is always about the non-perturbative completion of the sum over manifold. That's somehow, there's a lot of mystery in that at this stage.
Excellent. Maybe that could be our closing point. So let's end that.